Here is something most people do not think about when they are building with AI. Every time you ask an AI a question and it gives you an answer, that answer is coming from somewhere. Some mix of training data, weights, and statistical patterns learned from the internet. Some of that information is solid. A lot of it is outdated. Some of it is just flat out wrong, and the model has no way to tell you which is which. Now imagine you are building a health tool or a diagnostic tool, or anything where the information you surface to your users actually matters. You cannot afford to have your AI hallucinating facts and dressing them up in confident language. You need grounding, you need sources, you need research. Today, we are building a plant disease diagnosis app. Users upload a photo of a sick plant, and our app tells them what is wrong and how to fix it. And the entire build, from the very first decision about what to build to the last line of code, is going to be grounded in peer-reviewed science surfaced through Consensus MCP. By the end of this video, you will have a working full-stack application, but more importantly, you will have a repeatable workflow for building with AI in a way that actually holds up. Alright, so here is where most builds start. You open Claude, you describe the thing you want to build, and you start going. And that is fine for a lot of projects. But today, we are going to do something a little different before we write a single line of code. The app idea is a plant disease diagnosis tool. You take a photo of a plant that looks off, you upload it, and you get back a diagnosis with treatment steps. By the end of this video, you will have a working full stack application. But more importantly, you will have a repeatable workflow for building with AI in a way that actually holds up. Sounds straightforward, right? But here's the thing. Plant pathology is an actual scientific domain. There are real researchers who have spent careers studying how to identify plant diseases, what the visual markers are, which treatments work, and what the accuracy limitations are for different diagnostic approaches. If I just start building this without understanding any of that, I might build something that looks great but gives users genuinely bad advice, and that is a problem. So before we touch cursor, we are going to spend time with Consensus and figure out what the research actually says. We are going to let the science shape the product. The first thing I want to do is actually ask Claude to help me think through the blind spots in this idea. Not the code, not the stack, just the conceptual gaps. What are the things I might get wrong if I build this naively? So let's type into Claude. I am planning to build a plant disease diagnosis app. Users upload a photo of a sick plant and get back a diagnosis with treatment recommendations. Before I build anything, help me think through the key assumptions I need to validate. What could go wrong? What scientific accuracy concerns should I have? What questions should I be asking that I probably am not asking? And I want to be clear about what I am doing here. I am not asking Claude to start generating code. I am using it as a thinking partner to map the territory before I dive in. This is a habit I have gotten into with complex builds, and it saves a huge amount of time. Okay, so Claude raises some really useful questions here. How accurate are vision models actually at identifying plant diseases in non-controlled conditions? Are there established classification systems we should follow? What does the research say about treatment efficacy for common plant diseases? And how do we handle cases where the model is genuinely uncertain? These are exactly the questions I do not want Claude to answer from its general training data. I want published research. So let us go to Consensus. Before we wire Consensus into our workflow as an MCP, I want to show you what this platform actually does, because it is genuinely different from anything else in this space. Consensus sits on top of over 220 million peer-reviewed papers. That is not blog posts, not forum threads, not SEO content farms, published scientific research from actual journals. And what makes it useful for builders is that it does not make you do keyword search and then go read 6 papers yourself. You ask it a question in plain English, and it synthesizes what the research says. With inline citations, you can click through to the original study. Let me run a search so you can see what I mean. How accurate is AI at diagnosing plant diseases from photos? So right away, we can see that the research shows deep learning models can hit above 90% accuracy in controlled lab conditions. But that accuracy drops pretty significantly in real-world scenarios with variable lighting, image angles, and background clutter. That is an important nuance. If I had just asked Claude this question without consensus, I might have gotten a confident-sounding answer that glossed over the real-world accuracy gap. The research gives us the actual picture. I can click any of these citations and go straight to the abstract of the original paper. Let me run one more before we talk about the MCP integration. What are the most common plant diseases that can be identified visually? So we are already getting something useful out of this. There is a known taxonomy of visually identifiable plant diseases. This is not something I should be making up based on my own garden knowledge. This is documented in research, and that list is going to become the foundation of what our app supports. Alright, so now I want to talk about the part that makes this workflow really different, because going to Consensus and running searches manually is already valuable. But the real power comes when you connect Consensus directly into Claude, so that Claude can query the research automatically as part of your conversation. That is what MCP enables. MCP stands for Model Context Protocol. Think of it as a standardized way for AI tools to reach out and pull in external data during a conversation. Instead of Claude only knowing what is in its training weights, it can now tap into live external sources when it needs to. And when Consensus is your MCP, that means Claude can query 220 million research papers in real time, pull the synthesized findings back into the conversation, and ground its responses in actual evidence. The difference in output quality is real, and I will show you that in a second. But first, let me walk you through the setup, because it is genuinely simple. You come to this page on the Consensus site, and then you add Consensus as an MCP server inside Claude. The configuration is basically just a JSON block that tells Claude where to find the Consensus server and how to authenticate. I will link the full setup docs in the description, but let me show you what it looks like in practice. Once you save that and restart Claude, Consensus is live inside your workflow. You will see it listed as an available tool when you start a conversation. And when Claude decides a question warrants a research search, it queries Consensus automatically and shows you what it found. Let me run a quick test so you can see it working. What does research say about the best treatment for powdery mildew on indoor plants? See that? It queried Consensus, pulled findings from multiple papers, and the answer comes back with specific citations. It is not just telling me neem oil works, it is telling me what the studies found, under what conditions, with what level of effectiveness, and where that information comes from. That is the difference between building on vibes and building on evidence. And that is the workflow we are going to use for this entire build. Before we jump into the research phase, let me lay out the full workflow so you know exactly what we are doing and why. Because the structure of this build is actually the point. The app we are building is almost secondary to the process. Stage 1 is ideation. We started this already. We used Claude to map the conceptual territory, identify assumptions, and figure out the right questions to ask. Stage 2 is validation. This is where we take those questions to Consensus and let the research answer them. We are going to run a series of targeted research queries that will directly shape our product decisions. What diseases should we support? What does the AI accuracy landscape look like? What features do users actually need in a diagnostic tool? We do not assume any of that, we look it up. Stage 3 is the build. We open Cursor and start writing actual code. But here is the key part. We do not close the Consensus loop when we start building. Every time we hit a decision point during the build, like what to put in our AI system prompt, or how to phrase treatment recommendations, or what confidence threshold to use, we check the research. The MCP is active throughout the entire build. This is what makes it a research-grounded workflow, rather than just a build that happened to use a research tool once at the beginning. Consensus is a continuous layer across the whole thing. The other thing I want to name before we dive in is what we are not doing. We are not building this app to be a medical device or a certified diagnostic tool. This is a practical consumer app that uses AI vision and research-backed information to give plant owners useful guidance. That framing matters because it shapes what accuracy standards are appropriate, what disclaimers we include, and what treatment advice is responsible to surface. The research will help us get that calibration right. Okay, let us get into the research phase. Alright, Consensus MCP is active. Let me start with the most fundamental question for this entire build. How accurate is AI at diagnosing plant diseases from images? And what does the research actually say about the factors that affect that accuracy? I am typing directly into Claude here. Using Consensus, find research on the accuracy of deep learning and computer vision models for plant disease diagnosis from leaf images. I need to understand what accuracy levels researchers are achieving, which model architectures perform best, what the gap is between lab accuracy and real-world accuracy, and what factors most affect diagnostic reliability. I am being specific on purpose. I am not asking how good AI is at this in general. I am asking for the architecture findings, the lab versus real-world gap, and the reliability factors. The more targeted your query, the more useful the synthesis you get back. Consensus is querying in the background. Let me read through this carefully because there is a lot here. Okay, a few things jump out immediately. First, the accuracy dashboard. Lab conditions, controlled environments, clean images, 95 to 99.9%. Field conditions, real-world use, 47 to 89%. Cross-domain generalization, meaning a model trained on one dataset applied to a different one, 33 to 68%. That is a massive range, and that range is the most important number in this entire build. Second, on architecture. Efficient net and dense net ensembles are consistently at the top of plant pathology benchmarks. These are not general image classifiers. They are architectures that have been specifically evaluated on this domain. Third, the factors that affect reliability. Dataset domain shift, lighting variability, background complexity, disease stage visibility. These are not edge cases. These are the everyday conditions that real users are going to be shooting in. These three findings immediately tell me three things about how to build this app. 1. We need a vision model that has been tested on plant pathology data, not just general image recognition. 2. We need to tell users upfront what image conditions produce better results, because the research shows it moves the needle significantly. 3. We cannot surface a single confident diagnosis and call it done. The research is clear that real-world accuracy is lower than people expect, and that users need to see that uncertainty surfaced explicitly. I am opening a product decisions doc alongside this. Every time Consensus gives us something that should shape the build, it goes in here. By the time we open Cursor, this doc becomes the spec. Next question, what diseases should this app actually support? I do not want to make a list from memory or intuition. I want to know what the research identifies as the most common, most visually distinct, and most practically useful conditions for a consumer diagnosis tool. Find research on the most prevalent plant diseases in home gardening and indoor plant contexts. Which conditions are most commonly encountered, and which ones have sufficiently distinct visual markers to be reliably diagnosed from photographs. The response gives us a clear tiered structure. Tier 1, highly visually distinct, best candidates for photo diagnosis. powdery mildew, rust, anthracnose, sooty mold. These have markers that are consistent and recognizable enough to be reliably identified from images. Tier 2, moderately distinctive but prone to confusion. Early blight and late blight are the key example here. The research flags that these are frequently misidentified even by trained agronomists because early stage presentations overlap significantly. Tier 3, very difficult to diagnose from photos alone. Root rot, most viral diseases. The visual symptoms are either subsurface or too variable to classify reliably from a single image. That tier 2 finding is a direct product decision. If two diseases are hard to tell apart even for experts, our app cannot return a single confident answer for those conditions. We need to surface the ambiguity explicitly. Something like, this is consistent with early blight, but could also be late blight at early stages. Here is what to watch for as it progresses. That framing is more honest and more useful than false certainty. Adding to the doc, 6 core disease categories, note on ambiguous pairs, decision to surface differential diagnosis rather than single answers for overlapping presentations. Next query. Every feature decision traced back to a published finding. Let me now pull all of this into a proper technical spec before we open Cursor. Based on all the consensus research we just surfaced in this conversation, write a comprehensive technical product specification for the plant disease diagnosis app. Include the app name and core concept, the supported disease categories based on research, the tech stack with rationale, the key features grounded in our research findings, the AI analysis logic including confidence, scoring, and differential diagnosis approach, the treatment recommendation strategy with severity-conditional logic, the pre-upload guidance requirements, the trust and transparency features from the UX research, and any known accuracy limitations we should disclose to users. Format this as a structured spec document I can hand to an AI coding assistant. Claude is generating this from the research we just ran, not from its general training data. That distinction matters. Look at what this spec contains. The differential diagnosis approach exists because the research showed that certain disease pairs are frequently confused even by trained agronomists. The confidence scoring exists because the UX research showed that users who see confidence scores have better calibrated trust. The severity conditional treatment logic exists because the treatment efficacy research showed that first-line recommendations depend on infection severity. Every feature has a lineage. This is the spec we are handing to Cursor. Research grounded, evidence-backed, and ready to build from. Alright, that is the research phase. 5 queries, 1 spec, every product decision grounded in published science. Now let me show you what we actually built from it. What is good, everyone, and welcome back. Today we are building PlantCheck from scratch, a full stack AI plant disease diagnosis app, and I want to show you exactly where we are headed before we touch any code. This is PlantCheck running live. The homepage is clean. A big headline, a subtitle explaining what the app does, and 2 buttons, Start Diagnosis and View History. Scroll down and you have a How It Works section in a dark card and 3 feature cards showing what makes this different from just asking an AI a question about your plant. Click Start Diagnosis. The upload page loads. At the top, you have 4 photo tip cards. These are not generic advice I made up. Every single one of these comes from a published research finding we pulled through Consensus MCP before writing a single line of code. Use diffuse natural light. Frame close on the affected leaf. Plain background. Multiple angles if symptoms are not clear. Below the tips is the drag and drop zone. I am dropping a photo of a corn leaf with visible lesions. Preview appears. Hit Analyze Plant. Watch the loading stepper. Step 1. Uploading the photo to InsForge storage. Step 2. Claude is reading the image. That is our AI analysis running through the Anthropic API. Step 3, saving results. The results page loads. Primary diagnosis: northern corn leaf blight caused by Xerohylum tersicum. Confidence at 82%. Severity badge showing moderate. There is a diagnostic note explaining what made this case slightly ambiguous. Then the visual marker section showing exactly what Claude detected in the image. Elongated elliptical lesions, cigar-shaped lesion morphology. These are not generic descriptions. These are the specific observations Claude made from this photo. Below that, the treatment panel with 2 tabs. First-line treatment and severe cases. The recommendations differ based on severity. Click History in the nav. The history page shows all 3 diagnoses on record, including the one we just ran plus 2 previous results for common rust. Each card shows the thumbnail, the diagnosis name, the date, the severity badge, and the confidence score. That is the full product. Now let me show you how to build it. To make this tutorial focused on the parts that actually matter, I have put together a starter repository. Opening the browser to GitHub. mensalbert/PlantCheck starter. This repo has all the UI already built. The pages, the components, the styling, everything you see in the demo is already wired up visually. What is missing are the 2 things that make this app actually work: the database and storage integration through InsForge and the AI vision integration through Claude. Those are the 2 things we are building today. Clicking the green code button and copying the HTTPS URL. We are cloning this into Cursor. Switch over to Cursor, open the terminal. Running, git clone, paste the URL, then a space and a dot to clone into the current folder. The terminal shows cloning into dot, receiving objects at 100%, resolving deltas at 100%. The file tree populates. We are in, expand the components folder. All the UI pieces are already written: confidence bar, diagnosis card, differential list, loading diagnosis, upload zone, and more. Open confidence bar.ess, a complete TypeScript component. Takes a score as a number prop, picks a color set based on whether the score is above 70, between 50 and 70, or below 50, and renders a labeled progress bar. This is done. We are not touching it. Same goes for every component in this folder. The UI is complete. What we are here to do is wire up the backend logic that makes these components display real data. Expand the app folder. Subdirectories for history, results, and upload, each with a page.txt inside. The layouts are fully built. Upload page renders the photo guide and the upload zone. Results page renders all the diagnosis cards and the treatment panel. History page renders the list of past diagnoses, all written, all styled. Expand the lib folder. 3 files. Types.ts contains all the TypeScript interfaces. The diagnosis result interface defines the exact shape of a row in our diagnosis table. This is what every component expects to receive. Then Gemini.ts, the AI integration. And InsForge is the database and storage layer. Both files have to-do stubs with detailed instructions. These are the 2 files we are filling in today. Open lib/insforge.ts. Let me scroll through the full scope. 6 to-do blocks. To-do 1, initialize the InsForge client, the connection object every other function will use to talk to the database and storage. To-do 2, save diagnosis. Takes a partial diagnosis result and inserts a new row into the diagnosis table, returning the created row with the generated ID. To-do 3, update diagnosis. Takes the diagnosis ID and a partial update object, finds the existing row and updates it with whatever fields we pass in. To-do 4, get diagnosis. Fetches a single row by primary key. This is what the results page calls when it loads. To-do 5, get diagnosis history. fetches the 20 most recent rows ordered newest first. This is what the history page calls. To-do 6, upload image to storage. Takes a buffer, converts it to a blob, pushes it to the plant images bucket in InsForge storage, and returns the public URL we store in the diagnosis table. 6 functions. These are the entire backend of this app. Once these are filled in, everything else works. Let us start building. The project is already open in Cursor. File Explorer on the left shows the folder structure with app, components, lib, results, and upload all visible. Terminal is open at the bottom. File tree is now populated. Let me open lib/types.ts first because this is the foundation everything else builds on. The diagnosis result interface is the shape of a full database row. Every field we are going to store is defined right here. Either string, created underscore at a string, image underscore URL as string, primary underscore diagnosis as string, confidence underscore score as a number, severity as a union of mild, moderate, or severe, visual underscore markers as a string array, top underscore possibilities as an array of objects, each with condition and confidence, treatment underscore first underscore line as a string array, treatment underscore severe as a string array, diagnostic underscore notes as string, and status as pending, complete, or error. This file does not change. Everything else in the app imports from here. Opening app/page.csx quickly. This is the home page and it is already built. Look at the features array and the steps array, the hero section, the how it works card. All of it is done. We are not touching this file either. Back to the terminal. Running npm install. The terminal is showing progress as it resolves and downloads packages. It adds 370 packages. Confirmed 0 vulnerabilities. Dependencies are installed. Open package.json. Look at what is in here. At Anthropic AI/SDK is our Claude Vision client. At InsForge/SDK is the entire backend in one package. Database, storage, auth, Next 16, React 19, and Geist for the fonts. That is the full dependency list. 4 packages, and we have everything we need. Now open .env.example. 3 environment variables. Anthropic underscore API underscore key, ins4g underscore base underscore URL, and ins4g underscore anon underscore key. In the terminal, running cp.env.example.env.local. That creates the local environment file. Opening .env.local in the editor. Navigating to console.anthropic.com. Going to the API keys section. Creating a new key, calling it plant underscore diagnose underscore app. The key generates. Copying it immediately because it only shows once. Back in VS Code, pasting the Anthropic key into the Anthropic underscore API underscore key variable. Switching back to the browser and navigating to insforge.dev. Logging into the InsForge dashboard, selecting the personal organization, clicking New Project, entering the project name, Plant Village Project, selecting the US East region. Loading screen appears while the project provisions. The dashboard comes up showing getting started instructions. Copying the CLI link command. Back in the VS Code terminal, running npx at insforge/CLI link with the project ID flag. Typing I to confirm installation of the CLI. Terminal output confirms the project is successfully linked to Plant Village project. Now going back to InsForge dashboard and navigating to project settings. Under the Connect tab, selecting API keys. Copying the project URL first, then the anon key. Back in VS Code, pasting insforge underscore base underscore URL and insforge underscore anon underscore key into .env.local. Environment is set up. The .env.local file is open and all three variables are populated. Anthropic API key, InsForge base URL, and InsForge anon key all have their values. Switching to the browser, the InsForge dashboard is open for Plant Village project. There is a connect project modal showing the project URL and the anon key. These are exactly the values that went into the env file. Now the database, navigating to the SQL editor in InsForge, pasting in the create table statement for the diagnosis table. Let me walk through what this creates. ID is a UUID primary key generated automatically. Created underscore at is a timestamp defaulting to now. Image underscore URL is text. That is the URL of the uploaded photo in our storage bucket. Primary underscore diagnosis, confidence underscore score as an integer, and severity with a check constraint, locking it to exactly the three values: mild, moderate, or severe. Visual underscore markers is a text array. Top underscore possibilities is JSONB because it is a structured array of objects with condition names and confidence percentages. Treatment underscore first underscore line and treatment underscore severe are both text arrays, and status has a check constraint for pending, complete, or error. Hitting run, query executes successfully. Switching to the database tab, the diagnosis table is now in the sidebar. Clicking it shows all the columns from the schema. No records yet because we have not run any diagnosis. That is expected. Moving to the storage tab, clicking create bucket, naming it plant images. The public bucket toggle needs to be on so the images can be served directly by URL. Clicking create bucket. Success toast appears. The plant images bucket is listed and ready. Back in VS Code. Opening lib/insforge.ts. Let me scroll through to show the full scope of what we are filling in today. There is to do 1 for initializing the InForge client, to do 2 for save diagnosis, to do 3 for update diagnosis, to do 4 for get diagnosis, to do 5 for get diagnosis history, and to do 6 for upload image to storage. Each one has detailed comments explaining exactly what it needs to do. We are going to work through all 6 of them, starting at the top with to do 1. This is the client initialization. Everything else depends on this single export. Const insforge equals create client with an object inside. Base URL set to process.env.insforge underscore base underscore URL with the non-null assertion operator because we know this value exists at runtime. Then a non-key set to process.env.insforge underscore anon underscore key. Close the object, close the function call. Then on the next line, export default insforge. But this is the object that every single database query and storage upload in this app will call through. Scrolling down to do 2, save diagnosis. The comments explain the shape. It takes a partial diagnosis result and inserts it into the diagnosis table. The file has the import at the top, create client from @insforge/sdk, and the diagnosis result type from /types. Scrolling down to do 6 at the bottom. This is upload image to storage. The function signature is already there. It takes file as either a buffer or a blob and a file name as a string, and it returns a promise of string. That string is the public URL. Right now the body just throws a not implemented error. Let me replace that, highlighting and deleting the placeholder. Now writing the real implementation. The reason we need to handle both buffer and blob is that the upload API route gives us a Node.js buffer from the file array buffer, but the InsForge storage SDK expects a blob. So we have to normalize it, type in let blob : blob semicolon, then the conditional. If buffer dot is buffer of file, we are in Node.js buffer territory. Inside the if block, we need to extract the underlying array buffer cleanly. Type in const copy equals file dot buffer dot slice open parent file dot byte offset comma file dot byte offset plus file dot byte length close parent as array buffer. The reason we slice rather than just using file.buffer directly is that a buffer is often a view into a larger shared array buffer. Slicing with the byte offset and byte length gives us just the portion we care about. Then, blob equals new blob with the copy inside an array. The else block handles the case where the input is already a blob. Typing else open brace blob equals file semicolon close brace. Now the storage call, typing const open brace data comma error close brace equals await insforge dot storage dot from open parent the string plant images close parent dot upload open parent file name comma blob close parent. The bucket name plant images is the exact bucket we created in the insforge dashboard earlier. That name has to match. Now the error handling. If error is truthy, throw a new error with the message from error.message. Then check if data.url is missing. If not, throw a new error saying upload succeeded, but no URL was returned. And finally, return data.url. That URL is the public read URL for the uploaded image. It is what gets stored in the image underscore URL column in the diagnosis table, and it is what the diagnose route will fetch to send the image to Claude Vision. Scrolling back over the completed function. Buffer check, slice to array buffer, wrap in blob, upload to the plant images bucket, handle both failure cases, return the URL. That is upload image to storage done. Back in lib/insforge.ts. Scrolling past the upload image to storage function we just finished at the bottom of the file, up to the save diagnosis stub near the top. There is a ghosted code suggestion showing the shape of what we need to write. Let me implement this properly. Save diagnosis is the function called by the upload API route the moment a user submits a photo. At that point, we do not have a diagnosis yet. We create a pending record in the database, so we have an ID to work with while Claude is analyzing the image. Deleting the placeholder error, starting to type const open brace data colon result comma error close brace equals await insforge dot database dot from open parent the string diagnosis close parent dot insert open parent data close parent dot select open parent close parent dot single open parent close parent. The chain here is doing 4 things: from diagnosis targets, the table, inserts data, adds the new row with whatever partial fields we pass in, selects tells Postgres to return the created row rather than nothing, single unwraps the array response into a single object. Now the error check. If error, throw a new error with the message failed to save diagnosis colon, then error dot message in the template string, then return results cast as diagnosis results. That's a saved diagnosis done. When the upload route calls this with image underscore URL and status set to pending, it gets back the full row, including the auto-generated UUID. That ID is what gets sent back to the front end, so it knows where to poll for results. Scrolling down to do 3, update diagnosis, highlighting and deleting the placeholder throw. By the time this runs, we have a diagnosis ID, a primary diagnosis name, a confidence score, visual markers, top possibilities, treatment recommendations, and we are flipping the status from pending to complete. Starting the chain, const open brace data colon result comma error close brace equals await insforge dot database dot from open parent the string diagnosis close parent, then dot update open parent data close parent. This passes in the partial object with all the fields we want to set. Then .eq open paren, the string id, id close paren. This is critical. Without this filter, the update would apply to every row in the table. The EQ call scopes it to the specific diagnosis record, matching the UUID we pass in. Then .select open paren close paren .single open paren close paren to get the updated row back. Error handling. If error, throw a new error. Fail to update diagnosis : then error.message. Then return result cast as diagnosis result. That is update diagnosis done. So now we have the full write path covered. Next, we need the read functions. lib/insforge.ts is open. Save diagnosis and update diagnosis are both done. Scrolling down to do 4, get diagnosis. The comments explain exactly what this needs to do. Fetch a single row by primary key and throw if it is not found. This is what the results page calls when it loads. Deleting the placeholder, writing the implementation. Const open brace data : result, error, close brace equals await insforge database from open paren, the string diagnosis, close paren select open paren close paren eq open paren, the string id, single open paren close paren. The select with no arguments returns all columns. The EQ filter matches the specific row by UUID. Single unwraps the array into one object. Error handling. If error, throw a new error. Fail to get diagnosis : then error.message. Then a second check. If not result, throw a new error with the message diagnosis not found. This covers the case where the ID is valid syntax but does not exist in the table. Then return result as diagnosis result. That is get diagnosis. When someone navigates to the results page with a diagnosis ID in the URL, this is the function that loads their data. Scrolling down to do 5, get diagnosis history. The comments say fetch the last limit rows ordered by created underscore at descending, newest first. This is what the history page calls to show the list of past diagnoses. Deleting the placeholder, starting to type. Const open brace data : results, error, close brace equals await, insforge database from open paren, the string diagnosis close paren select order, open paren, the string created underscore at an object with ascending, set to false, and limit method signatures. The ascending false flag is what gives us newest first ordering. Error check. If error, throw a new error. Fail to get diagnosis history : then error.message. Then return results with the nullish coalescing operator, falling back to an empty array, cast as diagnosis result array. The nullish coalescing is important here because if the table is empty, the SDK returns null rather than an empty array, and the history page maps over the result. Without that fallback, it would throw. Scrolling down to do 6, upload image to storage. The comments describe the 3 steps. Convert a Node.js buffer to a web-compatible blob, upload it to the plant images bucket, return the public URL. The buffer to blob conversion logic is already written from the earlier session. Picking up from below that block, typing the storage upload call. All 6 insforge functions are now implemented. The database is fully wired. Let us move on to the AI integration. Still in lib/insforge.ts, wrapping up save diagnosis and update diagnosis. Both functions are using the same pattern. Target the diagnosis table, change the operation, use select.single to get the affected row back, throw on error, return the results cast as diagnosis results. Now switching tabs to lib/gemini.ts, scrolling down to the Analyze Plants by Image Functions tab to do 7. Right now, it just throws a not implemented error. This is the most important function in the entire app. Everything before this was infrastructure. This is where the actual diagnosis happens. the function takes base 64 image as a string and MIME type as a string and returns a promise of partial diagnosis result. First thing to handle is MIME type validation. The Anthropic API only accepts 4 image types: image/JPEG, image/PNG, image/GIF, and image/WebP. HIC is not on that list. So before sending anything to Claude, we normalize the input. Type in const valid MIME equals, then a conditional expression checking if MIME type equals image/JPEG or image/PNG or image/GIF or image/web. If it matches any of those, use MIME type. Otherwise, fall back to image/JPEG. This handles HEIC and any other unsupported format gracefully rather than throwing before we even reach the API. Now the API call, type in const message equals await anthropic.messages.create with an object. Model is Claude Opus 4.5. Max tokens is 1024. That is enough for the structured JSON response we are expecting. Then the messages array with one item. Role is user. Content is an array with 2 blocks. First block is the image. Type is the string image. Source is an object. Type set to the string base 64. Media underscore type set to valid MIME. TypeScript autocomplete shows the allowed string literals here, and valid MIME satisfies all of them. Then dataset to base 64 image. Second block is the text. Type is the string text. Text set to plant underscore diagnosis underscore system underscore prompt. That constant is defined at the top of the file and contains the full 4-step diagnostic reasoning sequence we want Claude to follow. Now extracting the response. The content array from the API can contain different block types, so we need to filter. Type in const text equals message.content.filter with a callback checking that b.type equals the string text. Then .map extracting b.text cast to the right type. Then .join with an empty string. Then .trim, that gives us the raw text output from Claude as a single string. Now passing the JSON out of it. Claude is instructed to return only a raw JSON object, but there is always a chance the model wraps it in a code fence or adds surrounding text. So we use a regex to find the JSON object. Type in const JSON match equals text.match with the regex / open brace, open bracket, /s s close bracket, star, close brace, /. That dot matches across new lines. So it captures the full JSON object regardless of how many lines it spans. If JSON match is falsy, throw a new error saying Claude returned a response with no JSON object. Otherwise, wrap JSON.parse of JSON match at index 0 in a try catch. Cast the result as partial diagnosis result and return it. In the catch block, throw a new error that includes the first 200 characters of the raw text. So if parsing fails, we can see what Claude actually returned and debug it. That is analyze plant image done. The function validates the MIME type, sends the image and the system prompt to Claude Vision, extracts the text response, finds the JSON object in it, passes it, and returns it typed as a partial diagnosis result. The API route will spread that result into the update diagnosis call to complete the diagnosis record. Still in lib/gemini.ts, reviewing the analyzed plant image output. The regex extraction and JSON parsing are in place. The try-catch around JSON.parse includes the first 200 characters of the raw text in the error message. So if Claude ever returns something unexpected, we have something to debug with. Now opening the upload API route, expanding app, then API, then opening route.ts. This is the first API route. When a user hits analyze plant on the upload page, this is the first thing that runs. Its job is to receive the photo, validate it, push it to InsForge storage, create a pending diagnosis record in the database, and hand back the image URL and diagnosis ID to the front end. Starting the post function. Type in const form data equals await request dot form data. That passes the multi-part form data from the request body. Then const file equals form data dot get open parent the string image close parent as file or null. First validation. If not file, return response.json with an object containing success, false, and error set to the string no file uploaded with a status of 400. Second validation. Allowed underscore types is defined at the top of the file as an array of the accepted image MIME types. If allowed underscore types dot includes of file dot type is false, return 400 with invalid file type. Third validation. If file.size is greater than max underscore size underscore bytes, which is 10 megabytes, return 400 with file too large. Now generating a unique file name. The extension comes from splitting the original file name on dot and taking the last segment with a fallback to JPG. Then const file name equals template string with crypto.random UUID. Every uploaded photo gets a UUID file name, so there are no collisions in the storage bucket. Converting the file to a buffer. Type in const buffer equals buffer dot from awaiting file dot array buffer open close. Then calling the storage helper. Const image URL equals await upload image to storage open parent buffer, comma file name close parent. That is the function we just wrote in lib/insforge.ts. It handles the buffer to blob conversion and pushes the file to the plant images bucket, returning the public URL. Now creating the database record. Const diagnosis equals await save diagnosis with an object. Image underscore URL set to image URL. Status set to the string pending. Visual underscore markers as an empty array. Top underscore possibilities as an empty array. Treatment underscore first underscore line as an empty array. Treatment underscore severe as an empty array. And diagnostic underscore notes as an empty string. That creates the row. The status is pending because we have not run the AI analysis yet. The empty arrays are important because the database schema has these fields as non-null JSON columns, and the results page will map over them, returning the success response. Response.json with an object. Success true image underscore URL set to image URL, and diagnosis underscore ID set to diagnosis.id. That is the full upload route. The front end will take the diagnosis underscore ID from this response and use it in the next fetch call to /API/diagnose to kick off the Claude Vision analysis. app/API/upload/root.ts is done. File validation, unique file name, storage upload, pending database record, success response. That is all in place. Switching to app/API/diagnose/route.ts, this is the second route. The imports are already at the top. Next request from next/server, analyze plant image from @/lib/Gemini, and update diagnosis from @/lib/insforge. There is also the MIME underscore map constant and the get MIME from URL helper that reads the file extension of the image URL and maps it to the correct MIME type string. This route is where the actual AI analysis happens. The upload route creates the pending record and hands back an ID. This route takes that ID, fetches the image, runs it through Claude Vision, and updates the record with the full diagnosis inside the post function, passing the request body. Type in const body equals await request.json, then destructuring. Const open brace image underscore URL comma diagnosis underscore ID colon id close brace equals body cast to the expected type. If not image underscore URL or not ID, return response.json with an error message and status 400. Then assigning the outer variable. Diagnosis underscore ID equals ID. This is important because we declare diagnosis underscore ID with let before the try block, so the catch block can access it when updating the status to error. Now the timeout, type in const timeout promise equals new promise of type never with an underscore for the resolve parameter and reject as the second. Inside, set timeout calling reject with a new error of the string timeout after 25,000 milliseconds. The reason for 25 seconds is that Vercel serverless functions have execution limits. If Claude takes longer than expected, we want to fail gracefully. Mark the record as error and let the user retry rather than have the function hang until the platform kills it. Now the analysis promise, type in const analysis promise equals an async arrow function. Inside, const image response equals await fetch of image underscore URL. If not image response dot OK, throw a new error with failed to fetch image and the status text. Then const array buffer equals await image response dot array buffer open close. Then const base 64 equals buffer dot from open parent array buffer close parent dot to string open parent the string base 64 close parent. Then const mime type equals get mime from URL of image underscore URL. That helps us split the URL on dot and looks up the extension in mime underscore map. Then return analyze plant image open parent base 64 comma mime type close parent. Now the race, type in const analysis result equals await promise dot race analysis promise open close comma timeout analysis promise open close invokes it immediately. Promise dot race settles as soon as either the analysis completes or the 25-second timeout fires, updating the database. Const updated equals await update diagnosis open parent ID comma an object with the spread operator on analysis result and status set to the string complete close parent. The spread takes everything Claude returned: the primary diagnosis, confidence score, severity, visual markers, top possibilities, treatments, diagnostic notes, and puts it all into the update object. Then status complete marks the record as finished, returning the updated diagnosis. Return response.json of updated. Now the catch block. If an error occurs and diagnosis underscore ID exists, call update diagnosis to set the status to error. This ensures the results page never gets stuck in a permanent pending state. Then checking the error message. If it equals the string timeout, return a 504. For any other error, return a 500. That is the full diagnose route. It receives the image URL and diagnosis ID, races the Claude Vision analysis against a 25-second timeout, spreads the results into an update diagnosis call, and returns the completed diagnosis. The front end redirects to the results page as soon as this resolves, reviewing the diagnose route one more time. The promise.race, the update diagnosis call, spreading the analysis result in with status complete, the catch block handling the timeout case separately. All good, switching to the front end. Opening app/upload/page.tsx. This is a use client component. Imports at the top, use state, use router, and the local components, upload zone and loading diagnosis. The handle analyze function currently just throws a not implemented error. Let me replace that. This function is what runs when the user hits Analyze Plant. It is responsible for the entire two-step process. Upload the photo, then kick off the AI analysis while keeping the loading stepper in sync with what is actually happening. Deleting the stub, starting to write, first a guard clause, if not file, return early. No point running any of this if nothing is selected. Then the state initialization. Set error of null to clear any previous error message. Set loading of true to disable the button and show the stepper. Set steps with an array. Active, waiting, waiting. That lights up step 1 in the UI, the uploading photo step. Wrapping everything in a try block. Step 1, the upload. Creating a form data and appending the file under the key image. Then fetching post to /API/upload with the form as the body. Awaiting the JSON response. Error check on the upload. If not upload res.ok or not upload data.success. Throw a new error with upload data.error. Falling back to the string upload failed. If we get here, the upload succeeded. Updating the stepper. Set step of 0 and the string complete. Set step of 1 and the string active. The UI now shows step 1 checked off and step 2 active, analyzing with AI. Step 2, the diagnosis, fetching post to /API/diagnose. Headers with content type application /JSON. Body is JSON.stringify with an object containing image_URL from upload data.image_URL and diagnosis_ID from upload data.diagnosis_ID. This is the slow call. It is downloading the image from InSforge storage, converting it to base 64, sending it to Cloud Vision, waiting for the JSON response, and updating the database. This is where those 10 to 20 seconds in the loading stepper come from, awaiting the JSON response. If not, diagnose res.ok, throw a new error, with the error from the response falling back to diagnosis failed. If we are here, the analysis is done. Set step of 1 and complete. Set step of 2 and active. That shows the saving results step, then a 500 millisecond pause. Await new promise with an arrow function taking R and calling set timeout of R with 500. This just gives the user a moment to see the third step complete before the page changes. Without it, the transition feels too abrupt. Then router.push to /uploaddata.diagnosis_ID. That navigates to the server rendered results page where get diagnosis fetches the completed record and renders everything. Now the catch block, set error with the error message, falling back to the string, something went wrong. Set loading of false to re-enable the UI. Set steps with all 3 set to waiting to reset the stepper back to its initial state. That is handle analyze complete, upload, stepper update, diagnose, stepper update, pause, redirect. If anything in that chain throws, the catch block surfaces the error and resets everything so the user can try again. In the terminal running npm run dev, Next.js starts on localhost 3000 with TurboPack, switching to the browser. Navigating to localhost 3000, the home page loads. Know what is wrong with your plant. Powered by Claude 4.5 Vision. The hero section, the how it works card, the 3 feature cards, all rendering correctly. Clicking start diagnosis, the upload page loads. Photo tips for better accuracy at the top. Dragging images.jpg from Finder into the drop zone. The preview appears with a thumbnail of a corn leaf showing brown lesions. Ready to analyze? Clicking Analyze Plant. The loading stepper activates. Step 1. Uploading photo. The call goes to /API/upload. The image gets stored in the InSforge plant images bucket, and the pending record gets created in the diagnosis table. Step 1 checks off. Step 2, activate, analyzing with AI. This is the slow part. The diagnose route fetches the image from storage, converts it to base 64, sends it to Claude Vision with the system prompt, waits for the structured JSON response, and updates the database record. Step 2, checks off. Step 3, saving results. Brief pause, then the page navigates automatically. Results page loads at /results/the diagnosis ID. Primary diagnosis: northern corn leaf blight, Exerohilum toxicum. Confidence at 82%, shown as both the number and the filled bar from the confidence bar component. Cut this part out. Severity badge showing moderate. Then the visual markers section: cigar-shaped necrotic areas, lesions 2 to 6 inches in length, exactly what Claude detected in this image. Treatment panel below with the 2 tabs: first line recommendations in the first tab, severe cases in the second. Clicking history in the nav. The history page loads and calls get diagnosis history from lib/insforge.ts. One result in the list: the corn blight diagnosis, the date, and the confidence score.